Hello everyone, I am Abhishek HR. Welcome back to the online session on dynamics of machine. In the previous session, we have learnt about the concepts related with the forced vibration. In your syllabus, in module 4, that is forced vibration, the last concept is critical speed. In today's session, I am going to explain about the critical speed. Before going to learn or before going to study anything about the critical speed, just recall the concepts that you have studied in the EME subject, that is Elements of Mechanical Engineering. In that subject, you have learnt about the turbines, compressor and pumps. In some of the practical applications like turbines, compressor and pumps, there will be a heavy disc which is mounted on a flexible shaft, lightweight flexible shaft. Sometimes we call it as heavy disc as rotor. So that rotor is mounted on a lightweight flexible shaft. So there will be some unbalance in the rotor due to the manufacturing errors. So due to that unbalance, it will lead to some severe vibration. So with respect to that, in today's session, we are going to study the critical speed concept. So critical speed means the rotational speed of a shaft start to vibrate violently in transverse direction. The rotational speed of a shaft start to vibrate violently in transverse direction. For that we call it as a critical speed. I'll repeat once again. The rotational speed of a shaft start to vibrate violently in transverse direction. In transverse direction is called critical speed, or sometimes we call it as whirling speed. Whirling speed. So the rotational speed of a shaft start to vibrate violently in transverse direction is called critical speed or whirling speed. So due to this critical speed, we get some severe deflection or the amplitude of the vibration, so that will lead to the failure. So to avoid this or to eliminate the critical speed, we should know the natural frequency of the shaft. Suppose in the critical speed region, if the amplitude of the vibrations are excessively large, then the large amount of force will be transmitted to the foundation. Here foundation means what? The bearings. A shaft which is supported with the two bearings, no? So here foundation means bearings. So when your amplitude of vibration is excessively large, so then the force will be transmitted to the bearings, so that it will affect on bearing also, right? So to avoid this or to eliminate the critical speed, we should know the natural frequency of the system. Critical speed will occur due to the manufacturing errors of the rotor or the mounting on a shaft. There will be an eccentricity. So there are certain reasons. So because of that, we will get the critical speed. So as per this concept, in the critical speed concept, we have two conditions: critical speed of a shaft, lightweight shaft without damping, and critical speed of lightweight shaft with damping. Now we will start with the critical speed of light shaft without damping, means without considering the damping. We are going to see the condition for critical speed of the light shaft. So here we have two figure 1 and figure 2, right? See, this is a axis of rotation. Now the shaft is in steady state condition. So the axis of rotation and shaft is on the same line, and this is a heavy disc, or sometimes we call it as rotor also. It is nothing but rotor. So it is mounted on the shaft. The point O is nothing but the center of the axis of rotation, and G is the center of gravity of the rotor, and this small e is nothing but eccentricity between O and G. So because of this, it will be leads to the some failure, and the shaft is supported with two bearings. The shaft is supported with two bearings, but it is in steady state. It is in steady state condition. Now, after shaft starts to rotate, so we have, after shaft starts to rotate, so the rotor is going to change its position. So here, once the shaft starts to rotate, the rotor is going to rotate, and the distance from O to E is nothing but the deflection. So that is denoted by Y, small letter Y. And here the center of gravity from the point E. Why? Because now the position of the rotor is changed, and center of gravity and from the point E is nothing but eccentricity, that is denoted by small letter E, and small w is nothing but the angular velocity or the angular speed of the shaft, and these are the two bearings. This is in steady state condition. This is when the shaft start to rotate. Now just denote this parameters K. So here radial stiffness of the shaft will denoted by K. Radial stiffness of shaft. Radial stiffness of shaft. Then E, small letter e, eccentricity. And point E. E is nothing but the additional displacement after the shaft start to rotate, the additional displacement from the axis of rotation. Point O means from the axis of rotation. From the axis of rotation. From the axis of rotation. Then we have O. This is the center of axis of rotation. Center of axis of rotation. Then we have G, center of gravity of the disc or the rotor. Center of gravity of the disc or rotor. Then M, it is the mass of the disc. Mass of the disc. Omega is the angular speed, and omega suffix small c is the critical speed. Critical speed. We have Y, that is the deflection from the axis of rotation. From the axis of rotation. So these are the notations that we are going to use while deriving this condition. Small k, radial stiffness of the shaft. The shaft that we have considered lightweight shaft. So the radial stiffness of the shaft is denoted by K, and small letter e, that is the eccentricity, a gap between the axis of the rotation and the CG of the disc. Then O, that is the center of the axis of rotation, and G, center gravity of the disc, and M, mass of the disc, omega, angular speed, and omega c is the critical speed, and Y is the deflection from the rotation. So you should be very careful while drawing this figure, because figure 1 is in steady state condition and figure 2 is in the after certain displacement we have drawn this figure with respect to figure 1. Now the forces acting on the system here, the forces acting on the system, on this system are, one is centrifugal force, at G, centrifugal force at G, that is nothing but, centrifugal force means what? F is equal to m into omega square into r. But here we have, in place of radius we have deflection and as well as the eccentricity. So it will be m omega square r into y plus e, and we have one more, force resisting deflection, that is K into Y, means there will be some resistance. So the resistance means the stiffness of the shaft, so that is K, and into the deflection Y. So force resisting deflection is K Y. So we have the forces, two forces acting on this system. Now with respect to this, at equilibrium condition, in equilibrium condition, Ky is equal to m omega square into y plus small e. Ky is equal to m into omega square into y plus e. So Ky, m omega square into y, m omega square y plus m omega square into e, m omega square e. Shift this m omega square y into left hand side. So it will become Ky minus m omega square y is equal to m omega square e, So here y is common, K minus m omega square into e. Now y is equal to m omega square e divided by K minus m into omega square. Next, y is equal to, see here we have m omega square e by K minus m into omega square. So divide by K for both numerator and denominator in right hand side, So y is equal to m by K omega square e divided by K by K m omega square by K. Have just divided numerator and denominator by K. So it will become y is equal to, see, we know one condition, that is omega n is equal to square root of k by m. Here we have m by k, means 1 by omega n square, 1 by omega n square. So y is equal to, here already we have omega square, m by k means it is 1 by omega n square. So it will become omega by omega n whole square, omega by omega n whole square into e, into e. See here, m by k is nothing but, m by k is nothing but 1 by omega n square, omega n square. Here already we have omega square, so omega square by omega n square. So I have written omega by omega n whole square. Next we have k by k, so it will be 1, k get cancelled. So 1 minus, here also we have m by k, so it will become omega by omega n whole square. So if you shift this e to here, so it will become omega by omega n whole square divided by 1 minus omega by omega n whole square. So this is the final expression to find the deflection of the shaft, lightweight shaft under this condition, light shaft without damping. So based on this, means omega by omega n. Here I will tell you one thing, this is what the angular natural frequency, and here we are discussing about the critical speed omega c. So it will become omega c as the k by m, omega c is equal to k by m. So the expression will become y by e is equal to omega by omega c whole square divided by 1 minus omega by omega c whole square. Just replace the notation with the critical speed. Y by e is equal to omega by omega c whole square by 1 minus omega by omega c whole square. So based on these values, omega by omega c, so there are certain conditions. I will just show you here. So this will be the amplitude ratio, that is y by e, and this will be omega by omega n. Okay. So if omega by omega is equal to omega c or omega n, if omega is equal to omega, if omega is equal to omega c, means resonance is going to occur, which means it will produce severe vibration, and that will leads to certain damage of the parts. So when omega is equal to omega c, we will get the severe vibration characteristics. Suppose if omega is less than 1, if omega is less than 1, then here the number or the factor omega by omega n square will become a very small number, and will get the positive value, So I can show you here. This is the initial condition 0. Suppose if omega is greater than 1, so then we will get negative value. If omega greater than 1, so we will get negative value. So This is how we are going to show the graph based on the critical speed condition. If we get omega is equal to omega c, means it is a resonance condition, means definitely we will get the severe vibration. It will leads to infinite. Then if omega is less than 1, suppose if we get a small number, means we will get some positive value. So that I have shown here, positive value. And if omega is greater than 1, so we will get the negative value. So that I have shown here. So this is how the amplitude ratio and the angular speed is going to vary. So this is all about the critical speed of light shaft without considering the damping. Okay, now we will see the critical speed of light shaft with damping. But now by considering the damping effect, we are going to derive the condition for this case. And here the damping means it is nothing but the air damping. So by considering the air damping, we are going to derive the condition. And as we know, so a lightweight shaft is connected between the bearing. So when we are going to rotate it, so I have just drawn the free body diagram, but you should remember one thing, I have not written the denotations here because I have already explained in the previous condition. But while you are writing in the exam or while writing in the internal assessment, you should write the notation for each condition, case 1 and for this case also. And here this is the steady state condition, means we have not rotating the shaft. Initially the shaft is at the stationary. So once the shaft start rotate, so this is indicating the displacement of the rotor. So this is the point O and this is the point E and this is G. O is what? The axis of the rotation, and Y is what? The deflection. And we are considering the damping effect. So at this point, means after rotating the shaft, the rotor is going to rotate. So there you will get a different direction. Why? Because here we have 4 forces acting on the system. The forces acting on the disc are, means on this system, the centrifugal force me omega square at G radially outward, me omega square, and the centrifugal force my omega square in the direction of OE radially outward. So in the direction of O and E towards the radially outward, means due to the centrifugal force. And the restoring force Ky, there will be some resisting offered by a body, so that is the Ky due to flexibility of the shaft. Next we have damping force here at point E, that is denoted by Cwy at E. So damping force. So there are totally 4 forces are there. So coming to this point at point E, means while the rotor start rotating, so in this direction we have a phase angle phi. I will just show here because it is very small portion in this figure. So it is like this, and this is the angle phi, and this is the eccentricity between E and G, So with respect to the phase angle, we have a direction of displacement. In the direction of displacement, it is me omega square into cos phi, and here perpendicular to this it will be me omega square into sin phi. So due to these forces O, E and G are not on the same line. Why? Because here we are considering the damping effect. So in the previous condition we have not considered the damping effect. So all the three forces are on the same line, which means collinear. But here O is here, E is here and G is here, means they are not collinear, not on the same line. So for this we have a two condition with respect to this. Resolving the forces along the direction of the displacement, as I said, resolving the direction of rotation. So with respect to this, me omega square into cos phi and with respect to the resisting force we have ky. So ky minus m omega square y is equal to me omega square into cos phi. Ky is here, means radially inward towards point O, and here also we have my omega square in the direction of the rotation, my omega square. So minus m omega square into y in the direction y into omega square, m omega square into y, that will be equal to the displacement of the direction of the displacement me omega square into cos phi. So ky minus m omega square y is equal to me omega square into cos phi. So if you resolve the forces along the direction of the displacement, so here we have the resisting force radially inward, that is what, the ky, and also we have in the direction of motion we have my omega square, and with respect to the direction of displacement, so that will be equal to me omega square cos phi, since we have the phase angle phi here. So ky minus m omega square y is equal to me omega square into cos phi. Just take out the common factor as y. So y into k minus m omega square is equal to me omega square into cos phi. So that will be represented by equation number 1. Now resolve the forces perpendicular to the direction of displacement. Now we have resolved the force along the direction of movement. Now we will consider the perpendicular. Perpendicular means we have me omega square into sin phi. So here one more damping force over here. So it is opposite to the me omega square into sin phi. So c omega y is equal to me omega square into sin phi. Just I am resolving the forces. So now we have two equations, equation number 1 and equation number 2. Just add this equation and squaring on both sides for these two equations. So we will get y square of k minus m omega square whole square plus cwy, here left hand side we have cwy, that is the damping force, into whole square is equal to me omega square whole square into sin square plus cos square phi. Why? Because here we have me omega square into cos phi, here we have me omega square into sin phi. So me omega square is the common factor, the remaining term sin square phi plus cos square phi. So after this divided by k, so y is equal to, means it is y square. Now I will reduce to y, means it will shift to the right hand side, it will become under square root. So it will become m by k, I am dividing by k both denominator and numerator. So once the square will shift to the right hand side, it will become the square root. So it will become m by k into e omega square divided by square root of k by m minus m omega square by k whole square plus cw by k whole square. Now just simplify this. As we know, m by k is nothing but 1 by omega n square. So here it will become omega by omega n. Why it is omega by omega n? Because already we have omega square here, and here we have m by k, that is 1 by omega n. So means 1 by omega n square. So omega square by omega n square, or else we can write omega by omega n whole square. And e I have shifted to left hand side, so y by e, just to show the amplitude ratio, and remaining factor square root of 1 minus k by m will be K. So K will get cancelled. So 1 minus omega by omega n whole square plus Cw by K. So in the previous concept, we know the value of Cw by K is nothing but 2 zeta into omega by omega n whole square. In the previous condition, we have solved and we got the value of Cw by K is equal to 2 zeta into omega by omega n whole square. So the final expression of the deflection of the shaft, that is y by E is equal to omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta into omega by omega n whole square. So this is the expression for the lightweight shaft by considering the damping effect. Now also we have phase angle. We should also show the condition for phase angle also. Now for the phase angle, divide equation 2 by 1, so we will get the phase angle condition. So here we have y into k minus m omega square and here we have Cwy. So y will get cancelled, so it will become Cw by k minus m omega square. So sin by cos phi will become tan phi. Sin by cos phi become tan phi. So tan phi is equal to value of Cw is 2 zeta into omega by omega n and k minus m omega square value is 1 minus omega by omega n whole square. So this is the condition for phase angle. Both the expressions, deflection as well as the phase angle, we are going to use while solving the numerical problems. And condition for the phase angle, if phi is equal to 0, which means omega is lesser than omega n, so the heavy side is outward, means the center of gravity of the disc will be outside. And if phi is 90 degree, means omega is equal to omega n, that is nothing but the resonance condition, that is we call it as a critical speed. If phi is equal to 180 degree, which means omega is greater than omega n, so it will be heavy side is inside, means since the omega is greater than omega n, the Cg will be inside, it will be located inside. So these are the conditions of the phase angle. Just recall this condition. So initially the shaft is at steady state condition. So once you start to rotate the shaft, so you will get the displacement of the rotor and the shaft. So for that I have drawn the free body diagram. So from this I have got the 4 different forces, that is centrifugal force due to me omega square into cos phi, me omega square at G, that is radially outward, and centrifugal force my omega square in the direction of radially outward, and the resisting force ky due to the flexibility of the shaft, and the damping force Cwy at E. So these are the 4 important forces. So based on this we can derive this condition. Now in the next session we are going to solve some numerical problems based on these 2 cases of critical speed.